We're now going to talk about a really useful couple of sections, sections 2.4 and then jumping way ahead to 8.1. We talk about systems of linear equations, and then in 8.1 we pick up the idea of a matrix and how we can use matrices to solve these. So we all know how to graph and think about something that looks like this. This is just a function. It's if we graphed it, it would be a straight line. From right here, we know that we would have a slope of -2, and from right here, this 5 would tell us that it intersects the y-axis at 0, 5. So we pretty much know everything about this guy right here. What we're going to be introduced to in this section is when we have multiple linear equations and thinking about how they interact with each other. So now the new thing is that we see systems of linear equations. And a system of linear equations will look something like this. We have this, oftentimes they're written with a little bracket to the left to kind of indicate that these guys go together. But we have multiple linear equations. Here we've got 2 of them. And in this section, we're asked to solve a system of linear equation. What the heck does that mean? So what does solve a system of linear equations means? It means to find the values that make both statements true. Find an x and find a y that make this guy true, and that same x and that same y need to make this true. And it may be that there's no place that makes both of these true. It may be that there's one time that both of these are true, and it may mean that there are several times, several solutions that would make both of these true. So it means find an x and a y that make both equations true. So I'm actually going to tell you what the solution to this system of linear equations is. So the solution to this system is this right here, 3/4, 7/2. In other words, when x is 3/4 and when y is 7/2, both of these statements are true. So let's just double check that real quick. So the first equation is y equals -2x plus 5. But I'm going to replace the x with 3/4, and I'm going to replace the y with 7/2, and I'm going to see if that is a true statement. So let's see, this on the right side would be -6/4. So -6/4 plus 5. And let's see, 5 is the same as 20/4. So this is -14/4, which is not -14/4, it's +14/4. +14/4 is 7/2. Yeah, 7/2 equals 7/2. So this these x and y values definitely work for the first equation. Let's check the second equation. And my second equation is y equals 2/3 x plus 3. So y equals 2/3 x plus 3. But I'm going to replace my x with 3/4. Because if it is a solution, it should work for this equation. I'm going to replace my y with this guy, 7/2. Okay, so let's figure this out. On the right side, these 3's will cancel. I have 2/4, which is 1/2. So 1/2 plus 3, that's 1/2 plus 6/2, and that's 7/2. Good, it works for the second equation also. So this really is a solution for this system of equations. Now, this is actually the only ordered pair x and y that will work in both equations. There's a lot of other ordered pairs that would just work in this one. For example, if x was 1 and y was 3, that would work. If x was 2 and y was 1, it would work for the top equation. But those pairs won't work for this guy. This is the only one, this 3/4, 7/2, that work for both equations, that make both of them true. And so that's a very special point for this system. It's the solution to this system. Okay, so we've kind of talked about what it means to be a system of linear equations and what the solution would mean. The rest of the section we're going to spend talking about actually how to find this. You know, I just spit this out and gave it to you, but the real work of these sections is being able to find the solution to a system. So this solution makes both equations true, and like we just talked about, it's the only solution. Let's take this system of equations here and graph both lines and see what that looks like. Okay, we're here in Desmos and we're going to graph y equals negative 2x plus 5. That's that first linear equation. And then the second one was y equals 2/3 x plus 3. Okay, so we have these two lines, the green one and the purple one, and there is this point that they intersect at. Okay, so this is no coincidence that this point that they intersect at is the solution to the system. It's the one point that both of them have in common. It's the one ordered pair that works for both equations. So when I graph this system, their point of intersection is the solution to the system. So when these are graphed, the solution to the system is where the graphs intersect. Now we were calling it, back here it was 3/4, 7/2. Well, this is just written in decimal form, 3/4, 7/2, so it's the same thing. This is the solution here. For the next example, we're asked to solve the system 3x plus y equals 20 and x plus 2y equals 5. So again, we're interested in knowing where both of these lines, what they share in common. So we'll go ahead and graph. The first one was 3x plus 6y equals 20. 3x plus 6y equals 20. So there's that graph there. And then the second one was x plus 2y equals 5. Okay, and so we look for a point of intersection. And these lines, you could follow them forever and ever and ever and ever, either direction. They're never going to intersect. And so this happens sometimes, that you'll get a system of equations where there is no solution. There's no point that they share in common. So when we graph these, we find that they are parallel lines. And we know that they will never intersect. They will never intersect. So this system here has no solution. There's no point that they share in common. So there is no solution. There is no point that would work for both equations. You can look and look and look and you'll never be able to find one. Another name for a system that has no solutions is an inconsistent system. So when you see that phrase, you'll know that this is a system that has no solution. Inconsistent system. And it just represents, in this two-dimensional case, it's just two parallel lines that are never going to intersect. Okay, let's get some more practice solving systems, and here's our next system. We'll take this and go over to Desmos and graph both of these lines. So I've got my first equation, 3x plus 6y equals 18, and then we'll put in x plus 2y equals 6. And okay, so something kind of new happened. The red line turned into a green line. What happened was these are actually the same line. Let's take off the green line for a minute and take off the red line. Okay, so when I put back on the red line, it's sitting right there. And then when I graph the green line, bam, it's right on top of it. These two equations are actually representing the same line. And that happens sometimes. So in this case, when we tried to solve this system, what we got were two lines that were sitting right on top of each other. Even though they don't look, they're written in different forms, they're representing the same line. So these two lines are the same. And so obviously these two equations have many points where they intersect. Anywhere along the line, they keep intersecting, right? So this is a case where we have many solutions. And when you have many solutions, that's called a dependent system. So in the last three examples, we had these three different systems of equations, and we were asked to solve them. And when you look at them, you can't tell, which ones are going to work out, which ones aren't. But what we found was this guy here had one solution. So its solution was 0.75, 3.5. It was the one place that both lines intersected. And sometimes you'll see this described as a unique solution. Just that word indicates, hey, there's only one of them. There's just this one point where they intersect. And then this system, do you remember what happened with this system of equations? So with this system, we graphed it and we found that they were these two parallel lines that were just never going to meet up. They're never going to cross. They're never going to have anything in common. So there was no solution. And the name for this type of situation is we have an inconsistent system. There's absolutely no point that would work for both equations, so it's inconsistent. And then you probably remember what happened with this third guy. We graphed both of these lines and we got what looked like, just one line, and it in fact was, because both of these actually represent the same line. So this is a case where we have tons of solution, tons of points where both lines intersect, and so the system has multiple solutions, so many solutions. And when we run into this situation where we have many solutions, it's called a dependent system. When you have any system of linear equations, these are the only three things that could happen. You're either going to get one solution, and that's actually the most common thing that's going to happen, is they're just going to cross at a certain one point. Or you might have an inconsistent system where there's no solution, or you could have a dependent system with multiple solutions. But these three are the only things that can happen. And this guy here is the most common case. So we have just explored and learned how to solve systems of linear equations graphically. We're now going to look at solving systems of linear equations using matrices. So before I tell you too much about what even a matrix is or how we're going to use it, I want to look at an example, and I want you to notice, just see what you can notice from this example. Okay, so say that our problem, our example, was solve the system x plus 2y equals 8 and 2x minus y equals 6. Well, we have just learned, we would know how to solve this. We would just throw them both into a graph and see where they intersect. Okay, I want you to just look at this object here and notice what this object has to do with this system of equations. The first thing you probably notice are there's these little brackets, these square brackets. And this is kind of indicating to us that we're looking at an array of numbers. We've got some rows, we've got some columns, but these numbers are arranged in this sort of rectangular grid pattern. And you probably notice where each of these numbers is coming from. This is the coefficient on the x, this is the coefficient on the y, and this is the constant term from this first equation. In a similar way, this is the coefficient of the x, this is the coefficient of the y right here, and this is the constant term for the second equation. So these are all the coefficients on x, these are all the coefficients on y in this column here, and in this third column are all the constant terms. Okay, so this rectangular box sort of gives all the information for this whole system. It's just like we've shed the equal signs and some of the variables, but we know what they represent because of where they are in the array. Okay, this is called a matrix. And this specific matrix is called an augmented matrix. And what it means is when you have a system of linear equations, and you put them in a matrix, including the constant terms over here. This is called an augmented matrix. There's another matrix that you'll see in future classes that's called just the coefficient matrix, and that would be just this part here, just the coefficients leaving off the constant terms. But for our purposes here in this section, we're going to use what's called the augmented matrix, which is the whole shebang, the whole thing. And so when you see this phrase, this is what it represents. It means that you've got a matrix where every piece of that equation is represented. Okay, so we've got this augmented matrix. How is this going to help us? With this matrix, a person is able to do a series of steps that are legal to change things around a little bit and make it so that you can change it into another matrix where it's easy to read off the solutions to the system of equations. So the reason we put the numbers in this matrix is to be able to manipulate the matrix, manipulate the numbers, but manipulate them in a way that the solutions don't change. So we put this matrix through a series of elimination steps. At this point, I'm going to pause and show you exactly what those elimination steps mean. So I've taken some work from a different problem to kind of show you some of the steps that are involved. We're taking this thing called a matrix, and we're going to, I said, put it through a bunch of elimination steps. And what that means is you're adding certain rows, you're multiplying certain rows by constants, you might be swapping rows, but the whole goal ultimately is to get something with a diagonal of ones and some zeros beneath and some zeros above. So this elimination steps, we're not going to go into a lot of detail because your calculator will do a lot of it, but there's a lot of arithmetic going on in those elimination steps. So we're going to let the calculator do these elimination steps, and I'm putting this down here just to remind us that there's actually quite a bit of work that's going on in this one step that our calculator is doing for us, but we're going to let it do the work. And we ask the calculator to put this matrix in something called reduced row echelon form. And when you look on your calculator, we'll take a look in just a minute, you're going to look for something called RREF. Once the calculator does this operation for us, putting this matrix in reduced row echelon form, what the calculator gives us and what the system results in is something that looks like this: 104, 0, 1, 2. Now we remember that this first column represented coefficients of x, and this second column represented coefficients of y, and this third column represented constant terms in the equation. So this first row right here is saying 1 times x plus 0 times y equals 4. So 1 times x plus 0 times y equals 4. Another way to read that is that x equals 4. Okay, the second row is saying that 0 times x plus 1 times y equals 2. So 0 times x plus 1 times y equals 2. And that's saying that y equals 2. This is the solution to the system, 4, 2. So the solution to this whole system is 4, 2. And we've found that out using matrices instead of using the graph of the system. Let's just double check here. Okay, x equals 4 and y equals 2. 4 plus 2 times 2, that's 4 plus 4 equals 8. Yep, that works in here. Let's take this and put it in here. 2 times 4 is 8 minus y equals 2. So 8 minus 2 equals 6. Yep, it works for both of those. So now let's go back and I'll show you exactly how on a TI to do these steps here. So this is similar to what your TI calculator will look like. This right here, this little matrix button, it's a second button. So we'll hit second matrix, and that's going to give us a certain menu. So I'm going to hit second matrix, and I have names, math, and edit. Those are my 3 different menus. I'm going to go to edit, and I'm going to edit matrix A, and the very first thing I have to do is tell it how many rows and columns. So I'm going to go up here, and so this matrix has 2 rows and 3 columns. So we say that it's a 2 by 3 matrix. So I'm up here, number of rows, it has 2 rows. And then I hit number of columns, there are 3 columns. And then I'll hit enter. And so the calculator, oops, somehow okay, we have 2 rows, enter, and 3 columns. Okay, enter. So now the calculator is waiting for me to put entries in, and we're just going to put in that last example. 1, enter, 2, enter, 8, enter, 2, enter, -1, enter, 6, enter. Now, importantly, I have to get out of this matrix, and the way to do it is hit second, and then the mode button is a quit button. So second quit will get me out of there. Okay, my matrix is in there, and so I go back to the matrix menu, second matrix, and now I want to tell it to do some math. And down towards the bottom there's that B says RREF, and that's the one I want. I want RREF. So I'm telling my calculator I want to do RREF. Now I have to tell it what matrix to do it on. Well, it's the matrix A that I just put in. So I'll hit second matrix. This time I'll go to names, and the matrix I'm interested in is that matrix A, so I'll click on that to pick it up. Okay, I've just told the matrix that I want to do a reduced row echelon form of the matrix A. It knows everything, so I'm just going to hit enter. And it gives me as the solution 104012. That's exactly what it should have been. Okay, so I input this matrix into my calculator, and then I ask the calculator to give me the reduced row echelon form of the matrix, and it spit out this. From this solution, I was able to read off what the solution to the system was. And that's the beauty of reduced row echelon form. It takes your data, your matrix in its original form, and reworks it through some legal moves that don't change the answer, and then it gives you a solution that you can just read off the solution. This says x equals 4 and y equals 2, and that's the solution to the system. Let's try another example. So we're asked to solve the system, this guy right here, and we're going to use matrices. So why don't you pause the video and see if you can input this into your calculator as a matrix, and then ask the calculator to perform reduced row echelon form, and it should spit out the solution. So the work you hopefully have already done is you put this information into a matrix, and then you're going to ask your calculator to perform reduced row echelon form for this matrix. And we'll go through this real quick just as another example of how to use the calculator. Second matrix, I'm going to edit a matrix. I want to edit matrix A. It's already 2 by 3, but I've got to override these values that are in here. So we'll put 1, enter, 4, enter, -1. Oops, that's not good. How about 1, 4, -1, and then 3, -2, 11. I'll quit, so second quit, second matrix, math, RREF, second matrix, names, A, enter. Okay, and this is the matrix I get out, 1, 0, 3, 0, 1, -1. So I had my original matrix, I asked the calculator to put it in reduced row echelon form, and the calculator told me that that form is 1, 0, 3, 0, 1, -1. From this, I can read off that the solutions will be x equals 3, y equals -1. So this is the solution to that system. If I were going to graph these two lines, I would see that this is their point of intersection. Okay, I have another example, solve this system, and using matrices, I'll put it in a matrix, 2, 1, 4, -2, -1, 3. I asked the calculator to put it in reduced row echelon form, and this is what I get out. I get 1, 0.50, 0, 0, 1. So something a little bit different is going on here. When I try to read off my solutions, the first line tells me that 1x plus 0.5y equals 0. Okay, that's not quite as helpful as it has been in the past. And then the bottom row tells me that 0x plus 0y equals 1. So 0x plus 0y equals 1. This right here is a big red flag because this is telling me that 0 equals 1. That can never be true. So this system here actually has no solutions because we've come up with a false statement. If you end with a row like this, where you have all zeros, but then a 1 at the end, that's telling you a false statement. It's telling you that 0 equals 1. And this original system will have no solution. It's an inconsistent system. If we were going to graph these two lines, we would find two parallel lines. So here we had a nice one solution. Here we have an inconsistent system. And there's one other case, a dependent system. What would that look like with matrices? So we're going to go ahead and solve this system. We're going to put it in a matrix and do RREF on it and see what the solution is. I put this information into an augmented matrix. I asked the calculator to put it in reduced row echelon form for me, and this is what I get out. This top line is saying that x plus 1/3 y equals negative, this is 1.33 forever, and then the bottom line is saying 0 plus 0 equals 0. Okay, this statement is true, but it doesn't help us a whole lot to get just one answer. This right here is indicative of a dependent system, a system where there are many solutions. So when we go through this process and we end up with a row of zeros at the end, we are in a dependent system. We have a system that has many solutions. So these are probably the same exact line, just sitting right on top of each other. We now take a look at an example where we're asked to solve a system where there are actually 3 equations and 3 different variables. And we are going to use matrices. And here in this example, we see the power of matrices. This is much harder to graph. We can't graph it in 2 dimensions. We can't use Desmos or anything to solve this. And so as systems get larger, as you have more variables, matrices are the tool that are going to enable us to solve these larger systems. We can't do this graphically with Desmos because that's a 2-dimensional graphing software. So we start by putting this in a matrix just like we were before, the coefficients 1x, 1y, 1z, and then the constant term. And then the second line would be 2, 3, 1, 3. The third line would be 1, -1, -2, -6. And so here we see that we have 3 rows and 4 columns. So this is a 3 by 4 augmented matrix. And we're going to take this matrix and we're going to enter it into our calculator. We'll have to tell the calculator that instead of a 2 by 3, we now have a 3 by 4 matrix. And we'll ask the calculator to do a reduced row echelon form, and we'll see what it gives us out. Once I ask the calculator to perform this operation, it tells me that all of those row operations result in this matrix. 0, 0, 1, 2 for the last. So a lot of work was going on in here. We just let the calculator do it. But this will tell us that 1 times x equals -1. So that tells us that x equals -1. And then this second row tells us that 1 times y equals 1. So y equals 1. And the third row tells us that 1 times z equals 2. And so z equals 2. This is the solution to this whole system. And another way that it's often written is as an ordered triplet, -1, 1, 2. So this is the solution here. And what we're going to do is we'll go back and just test it and make sure that this really does work in all of those cases. So -1, 1, 2. So -1 plus 1 is 0, plus 2 is 2. Yep, it worked right there. 2 times -1 is -2, plus 3 times 1, that would be 1, plus 2 is 3. Yep, that works there too. So this last one will test the solution. -1 minus 1, that's -2, minus 2 times 2, that's -2 minus 4 is -6. Okay, so this solution worked for all 3 equations here, and it really is the one and only point where that will work. And actually what this represents is these are planes in a line in 3 space. So, you know, you have these 3 planes, and there's one point where all 3 planes are meeting, and the point that it's meeting at is the point -1, 1, 2. That's what it's representing.